While discussing the architecture of a computer system, we discussed multi-processor systems where we had more than one processors. Now let's look at the architecture of an operating system. So we're going to first talk about a multi-programming system. Now the name resembles each other, but in the case of a multi-processor system, you have more than one processor. In the case of multi-programming, there could be one or more processors. This is not related to the number of processors. The key idea here is that a user is not fast enough to keep the CPU and or the I/O devices busy all the time. So if we have a computer system dedicated to one single user, most of the time the CPU and the I/O devices will remain idle. If we have paid so much money for the system, why not let multiple users use the system so that we get a better performance, a better efficiency or utilization of our computer system through multiple users. So this approach, which is also called a batch system, is used typically for systems like mainframes, for example, where you have many users sharing the same computer. This is different than what you already have on your computer because typically you're the only person who's using the computer at a time. And as we said, you're actually not able to utilize your CPU and memory all the time. But if we talk about a system like a mini computer or a mainframe where many users utilize the system, multi-programming will organize the jobs, which are actually the tasks, the code, the program, and the data together. That's called a job. So that the CPU always has a job in hand to execute. Now, as I said, alone, one single user cannot produce so many jobs. But if we have many users together, that could be possible. So we have many jobs and we take a subset of those jobs and keep them in memory. And we pick one of those jobs and run that job. This is called scheduling actually, because we select the job to go into the CPU. When that job has the need to wait, for example, that job wants to do I/O, then the operating system will switch to another job, which is called context switching, because you're changing the context from this process or from this job to another job. But not the important thing. We do the context switch. We switch from one job to the other when that process that was in the CPU needs to do I/O, or also, of course, if that job ends. An alternative approach, which is used in most modern computer systems and also on your computer systems, is what we call multitasking or time-sharing approach. In this case, the CPU switches between the jobs, not when the job needs to do I/O, but instead it switches between the jobs so fast that to the human being it appears like each job, each process has its own CPU, where all CPUs are running those jobs in parallel. In fact, there's a single CPU. And since we're doing context switching to multiple jobs, it appears like each job has its own share of the CPU. Really, they have their share of the CPU in the dimension of time. For example, we say, I'm going to give, say, 10 milliseconds of execution time to each job. Okay? So assume that we had 10 such jobs. Each one gets, for the sake of simplicity, equal time slots, 10 milliseconds. So in 100 milliseconds, each job would get a 10 millisecond CPU time. This would appear to the user as if the user had 10 CPUs which were running at the clock rate of 1 over 10th of what the user really has. So it's like 10 slower CPUs, but each process has its own CPU. To the user, it appears like all processes are running at the same time, simultaneously. That's not the reality. Since we have a single CPU, at any point in time, only one of them would be running. But since we immediately switch to the other one, to the human eye, it appears like they are running in parallel. This is quite important, especially when we're searching for interactivity. What we mean by interactivity is you're like at the moment I'm using my computer. At this very moment on my computer, uh, my PowerPoint is running. In addition, I have my web browser running, actually uploading the previous videos I have recorded to YouTube. Also, another process is running for video recording, and yet in the background, Dropbox and Google Drive are also running for synchronization. Now, my operating system is giving a time slot to each of these processes. The size of the time slot to each process, by the way, is actually different. And the number of time slots each process is taking is different. Okay, like probably at the moment, Google Drive and Dropbox are not getting too much time slots because heavily my PowerPoint and more heavy my video recording is running. Okay, so my CPU is actually splitting the time into smaller time frames, time slots, and giving to each one of these processes. And I want interactivity. What does that interactivity mean? Look at my mouse. Now I'm going to move my mouse to the upper right corner. And when I do that, the moment I move it, I want to see the change on the screen. Now, if the computer system was not interactive, it might have delayed this operation for several seconds. So I move my mouse, but I don't see the mouse pointer moving. So when I want to click it, I don't know where the mouse would be when I have clicked it. So this would really affect my performance. Probably I would be clicking something wrong. So I, in my computer system, I want interactivity. Performance is at the second rank in terms of preference. If I didn't have interactivity, if my mouse was moving not when I wanted, but overall, like my uploads, downloads, whatever, they were working faster. It wouldn't be something I would like because probably I would be like while trying to upload the video to YouTube, I would be clicking the wrong place because interactivity was not so good. So I don't care about how fast the video upload is going. The more important thing would be in such a personal system, more on interactivity. So interactivity depends on response time. And the response time typically should be much lower than a second. The response time means I do something and I get the result. And typically I want the result to be available as soon as possible. So each user has at least one program executing in memory. We can call this a job. or a process or a task, similar concepts. If several jobs are ready to run at the same time, then it is up to the CPU scheduler to decide which one to run next. So we call that scheduling, or more proper term would be CPU scheduling, because we're going to talk about other types of scheduling also. If the processes don't fit in the memory, now I have a problem. As I said, I'm running PowerPoint, my web browser, recording utility, Dropbox, Google Drive, and many other things in the background. So if the processes do not fit in memory, and since I have limited memory, one thing I can do is swap a process out. Swapping a process out is removing it completely from memory to some secondary storage, a place we call swap space. But note that for a process to be executing, that process should be in memory. So if I swap, not me of course, it's the operating system who's doing that swap out operation. But if the operating system decides to swap out that process to the swap space, that means it's not planning to execute that process in a short term. So this would be like suspending that process temporarily, not terminating it. Later it will be able to resume from where it was left. But for some time it means the CPU, the operating system is not planning to use it to run it, because if it were to run it, it should have been in memory, not in the swap space, not in secondary storage. Well, as I said, this would pause that program for a while, so that's not something very something I would like very much. So there is a better approach, which is called virtual memory. In the case of virtual memory, rather than keeping all processes in memory all the time, we keep the parts that are necessary for us at the moment. For example, at the moment, I'm using PowerPoint for my presentation, but I don't need, for example, spell check, because I'm not typing anything in PowerPoint. I'm just in the slideshow mode. So at the moment, spell check is completely redundant for me. So why keep it in memory and consume space while I have to swap out another process? So I will be keeping only the parts that are related to the slideshow in memory, not the whole PowerPoint. Similar for the other processes. So if only the parts that are required at the moment are in memory, I can fit more processes into memory rather than swapping them out. Okay, so this is a better approach. But note that there will come a point where with virtual memory, still I will not have enough memory. In that case, still swapping can be used. So don't think that since we have virtual memory, we don't have any swapping. We use both of them together. But one works for the shorter term, the other one works for the medium term. The memory layout of the multi-programmed system with a very, very simplistic approach is like this. Now, in reality, it's not like this, because in this figure, we're showing the jobs or the processes as consecutive chunks. So, in other words, that means I have instruction 1, 2, 3, 4, 5 for job 1, and 1, 2, 3, 4, 5 for job 2, whatever, for each job. Jobs could be of different sizes, but the whole memory space for a single job in this example appears to be consecutive. In reality, we will split job 1 into many pieces, so one part will be here, some here, similar for the others. But for the moment, let's take it simple and assume that all memory required for one job is in a consecutive chunk. In multiprogramming and multitasking, we require the operating system to be able to load the programs from the disk into memory in separate areas of the main memory. And we should also provide protection of one process or job from the other. In other words, job 2 should not write something in the area of job 1 and vice versa. We want to avoid it because this will cause another job to either crash or do something in an unexpected manner. It will even provide hacking. So this is something we would like to prevent. The operating systems we have discussed are typically interrupt driven, either hardware interrupts or software interrupts, which we call exceptions or traps. These software interrupts, for example, could be due to software errors like division by zero. If you try to divide a value by zero, your process will raise what we call a division by zero exception or trap, and that needs to be handled. A request for the operating system services, like you make a system call, say read this from this file or from the keyboard, whatever. And there could be other things like, as we said, job 2 tries to read or write from the area of job 1. So that would be, for example, a segment violation. Also, we make use of these exceptions and traps for communications between the processes. That's something we're going to visit later on. The operating system typically works in what we call a dual mode. There are typically two modes. One is the user mode and the other one is the kernel mode. That's why we call it the dual mode. And there's a mode bit which remembers in which mode we are. Are we in the user mode or the kernel mode? The kernel mode is what we call a privileged mode, because in the kernel mode you can execute some privileged instructions. Now, executing these instructions is very tricky, and if not handled properly, it may cause the system to malfunction, or even if you allow a regular user to execute privileged instructions, that user could hack the whole system. Therefore, we say these privileged instructions can be executed only in the privileged mode, which is the kernel mode. And the user applications typically run in the user mode. So this mode bit provides us the ability to distinguish when the user is running some user code, user program, or executing part of the kernel to do something on behalf of the user. In that, which is the case, we need some privileged access rights. The system call mode typically changes the mode from the user mode to the kernel. So when you make a system call, actually you're making the system call in the user mode. When the system call starts, it switches to the kernel mode. It does the necessary checks. Maybe you don't have the right to do this system call, or if you do it, it will cause a problem in the system. So the kernel makes those checks, if appropriate, fulfills the request, and before returning the control back to the user program, it switches back to the user mode before the system call ends, so that when the system call ends, the user code does not find itself by mistake in kernel mode, because in that case, he or she could apply all checks. So when you make the system call, you're in user mode, but the system call switches to the kernel mode, working kernel mode, and then switch back to the user mode. Lately, with the use of these virtual machines like VMware, Parallels, VirtualBox, whatever. Now, in your host, in your main operating system, say it was Windows, you would be, for example, in your user mode. Then in the user mode, you start a virtual operating system in the virtual machine. Say you're running Linux inside Windows. And in Linux, you're going to be at some point be executing some kernel mode operation. But that kernel mode operation is running in the virtual machine, but the virtual machine itself is in the user mode. So inside the user mode, you should be executing something in kernel mode but of the client or virtual operating system. So there are some tricks you could be applying here to deal with that. There's also what's called the virtual machine manager mode that's used for these guest virtual machines, but we'll not go into too much detail of that. So typically a system, as I said, in your user process, you would be executing your user process in the user mode. You make a call for a system call, and this will cause a trap. You were in user mode, therefore your mode bit was 1. This trap will cause a switch to bit 0. This is something you couldn't do directly yourself. Can be done only by this system call library. So you will switch to kernel mode, execute the system call typically in kernel mode. When you're done, before returning to the user process, the system call library will switch the mode back to 1, which is the user mode, and you resume the user process from where it was left. So it will be returning from the system call, but executing in the user mode. For example, this is being used for that time slot. Remember when we discussed time sharing, we said each process gets a time slot. Well, what if the user was able to go to the kernel mode and resetting its time slot? So the user process would acquire the CPU once and always extend its time slot and never leave the CPU. So that would cause a process hogging the resources of the whole system. So to avoid this problem, the timer is set so that it interrupts the computer after some time period. It's just like when the scheduler is giving the CPU to process P1, it will be running in user mode in process P1. Just before giving the control to P1, it will set the timer, say to 10 milliseconds, and give the control to process P1. While P1 is executing, it could do anything, whatever it wants. But while it was working, at some point, the timer will time out. And this will cause a system call while P1 is executing, so that system call will switch from the user mode to the kernel mode, and now the kernel is running, and the kernel says, oh, okay, the time slot for this process P1 has ended, so it will remove P1 from the CPU and bring, say, process P2 to the CPU and complete. This would be a context switch executed in kernel mode, and this way process P1 would not be able to prevent other processes execution. It could not steal the time slot of other processes. So that timer keeps a counter that's decremented by the physical clock. When that value reaches 0, the timeout will occur. It's the operating system that's able to set the counter. It's a privileged instruction, therefore P1 cannot change that counter. That's the nice thing. And as I said, when it depletes to 0, the operating system will generate the interrupt and do the context switch. And you set up before scheduling the process to regain the control or terminate the program that exceeds the allotted time.